All right, total requests. Okay, so previously we had defined work and kinetic energy, and we looked at an example where we had a mass in a gravitational field. And we lifted the mass up, lowered it down, and we calculated the work done by gravity. We found overall the work is zero. Gravity would do negative work as the mass was lifted, and positive work when it was lowered back down. So the box, or the mass, whatever it was, ended up in the same place it started, and the total work done by gravity was zero. Then we looked at another example where we had, basically the same mass. Let's say we push it to the right, and then push it back to the left. So here we have gravity. And we're calling the overall motion a loop, because we end up back where we started. So for gravity, the work done for this loop, whatever path takes you back to your starting point, that was zero. But then when we look at friction, we found that the work done over a complete loop was not equal to zero. And it's always going to be less than zero. So the idea is when you're going to the right, the work done by friction is negative because the force of friction is going to be to the left. But then if you push it back, the displacement's to the left, but now the force is going to be to the right. It's always the opposite direction that you're moving it. So in the case of gravity, whatever we did on the way up, it's kind of undone on the way down. With friction, that does not happen. And I want to look at another example with gravity, just to kind of reinforce this idea. Let's look at, we're going to calculate the work done by gravity along a different loop, where say we have our mass that starts on the ground. We'll call this corner point A, this is point B, and this is point C. So we're going to calculate the work done by gravity over a loop where we're going to start at point A, we're going to push it up the incline, then let it fall on the ground, and then push it back around, just across the ground. And calculate the work done by gravity on every step of the way, and then add it all up to find the work done over this loop. So we're going to start with the work done over this path AB. So when the mass is on this incline, the displacement, we'll just call that the x direction for now, that's delta x, and we want to calculate the work done by gravity. Force of gravity is straight down, so we have to break it into a component that's parallel to the direction of the displacement and a perpendicular component. So this is mg. This one here is mg sine of theta. And this one here, we don't care about. It's mg cosine theta, but who cares? Now we've done this enough time breaking it into components, so let's just move on. We can see that angle, this component has to be sine of theta. And so the force and the displacement are in opposite directions. And so the work is negative. And we have minus mg sine of theta times delta x. Okay. Now we're at the top of the incline. Let's just push it over, let it fall. The work from B to C. So again, when the box is falling, the displacement is straight down, and the force of gravity is also straight down. And so the work is going to be positive. Now we need to know this distance. Let's say this, actually, let's go back. Let's call this incline L and the height here H. So we'll call that displacement L. And here we're going to have plus mgh. And finally, now that we're on the ground at point C, let's push it back to A just across level ground. And the work done by gravity, in this case, is 0, because it's moving across the ground. Gravity is perpendicular to that, so no work is being done by gravity. So again, we're ignoring all the other forces acting here. Just focusing on the work done by gravity. And then the work done around this loop, let's write this off to the side. We have minus mg, I'm going to rewrite this a little bit, mgl sine of theta plus mg. Okay, now before we got 0, this time it looks like we might have something, but theta is the angle of the incline. We can see from this triangle, it's hard to see because it's so cluttered, but sine of theta is h over L. Or h is equal to L sine theta. And so if we replace this, L sine theta, with h, we can see that we have minus mgh. Sorry, I didn't write that down right. Minus mgh plus mgh. And we see again, we're getting 0 for this result. So we lifted it up, straight up, dropped it straight back down. We got 0. Here we do another path and we get 0. And you can do more and more of these if you like. You can picture like a square type of path. Like here's the ground, lift it up, move it over, lower it, back to the start. Every loop you calculate, we're going to find that the answer for gravity is 0. Now, technically, we need this to be true for every possible path. And the problem is it's kind of difficult to calculate over, we look at path where we can actually calculate, but what if we went over a circular path? That would be very difficult to calculate the work done by gravity. Like if you look at some point here, it's moving in this direction and gravity is straight down. But then here, it's like every point there's going to be a different relationship between the angle of the displacement and the force. And so we'd have to break this up into pieces and then add up all the pieces. That's a familiar process. You've seen it, many examples of this before. There's a reason Isaac Newton invented calculus. He needed to do physics. But if you look at the past, we can. And you might think, since this has to be true for every possible path, we can never actually prove that this result. What I'm saying here is that the work done for any loop, the work done by the gravitational force is 0. It might seem like that is impossible to prove, but actually it can be done, just not by us. If you want to prove that, you have to go up to at least like Calc 3. That's where you study vector calculus, and kind of be like the end of the Calc 3 class. So if you're planning on going there, there's something to look forward to. But there's a way to prove that for a force like gravity, the work done along any closed path is 0. And if that is true, if the work along any closed path is 0, we call that a conservative force. So I'm going to write that down. So what that means, in order for a force to be conservative, the work has to be 0 for any closed path. So if you take an object, lift it straight up, straight down, or you could take a slight detour around the Andromeda Galaxy, you have to get 0 either way. Of course, if you're going to go around the Andromeda Galaxy, the force would no longer be mg. You'd have to use Newton's law of gravity. So we're just going to accept that this is the case without proving it. But we can kind of test it with various shapes where we can calculate, and it always works out. Okay, now That raises the question, why do we care if a force is conservative or not? So let's say we have a conservative force. Okay, we have a conservative force, and let's say we take some loop. We have some path let's say we start at point A and go around the loop. I can definitely say that the work along this path is 0. Now let's say B is any other point on this path. So let's just say going from A to B, let's say that the work done by this conservative force is 1,000 joules. We'll just use a number, nice even number. Let's just say it happens to be 1,000 joules here. Then what is the work done by this force along the remainder of the path? Well, it's got to be minus 1,000 joules, because then we've completed the path, so these two have to add up to 0. Okay, now here's where the important part comes in. Let's consider going from A to B along this path in the reverse direction. So let's say we do this. Now we're following the exact same path as we took here, just in the opposite direction. Let's call this path 1, and this red one path 2. Well, the work along path 2 has to be plus 1,000 joules, because all we're doing is reversing the direction. So remember, if you force, let's consider a simple case where the displacement is to the right and the force is to the right, that would be a positive displacement. If you are a positive work, if you keep the same direction but just change same line, but just reverse the direction of the displacement, you get the same numerical value, it's just the opposite sign. And so the work along path 1, or the work along path 2, is also 1,000 joules. And so the key here is that the work along this path connecting A and B is 1,000 joules, and the work along this other path connecting A and B is 1,000 joules. They are the same. And that is the important result here. That's true for any conservative path, any conservative force. We could draw a third path connecting A and B. Let's call this path 3. The work along path 3 done by this force has to be 1,000 joules. Because we could trace it backwards and we'd have to get back to 0. So if we have plus 1,000, we'd have to have minus 1,000 going this way. So if we go this way, it's plus 1,000. And that is why conservative forces are so useful. Now, maybe you're not seeing why that's useful yet, but it allows us to give a definite answer. Like, say we have a conservative force, and I ask you, how much work is this going to do? Say we have a particle that's going to go from point A to point B. So we have some object that's going to move from A to B, and it's going to be acted on by a conservative force. Can I ask you, without giving you any additional information, well, you'd have to know, like maybe it's a force of gravity, you'd have to know what the force is, and these 2 points here. But I can ask you, what is the work done by this conservative force connecting points A and B? And you can give a definite answer. That's not going to be true in general, like for forces in general. Like, let's say this was friction. Let's say this is a top view. So you're looking down on an object. And I'll ask you, how much work is friction going to do as we go from point A to point B? You cannot answer that question without asking for more information. Like, how are we going from A to B? Because if we take a straight line, maybe the work done by friction is going to be, say minus 1,000 joules. But if we take a different path, we'll get a different answer. And that looks like two kind of distinct. Let's just say we take some different path here. Maybe that'll be minus 1,300 joules. Because it's a longer path. The longer you make it, the more friction, more work is going to be done by friction. And so you can't tell me what the work is between, like how much work the force did between these two paths, if the answer depends on the path. But for a conservative force, it does not. It only depends on the starting and ending points. And so we can define a potential energy function, which is a function of position. So a potential energy function is associated with a conservative force, and it only depends on location. So I'm going to talk about how to define potential energy. Potential energy, we use the value U for potential energy, which is measured in joules. Sometimes you'll see it written out like PE, and sometimes they go farther. They'll say like GPE for gravitational potential energy, but that's a lot to write in an equation. So I just call it U. Every book I've ever seen until recently calls it U. Some books spell it out now, but let's just say U is the potential energy function. And again, this has to be for a particular conservative force. So the way we define potential energy I'm going to write it down first. So really, what we're defining is a change in potential energy, which is related to the work done by that conservative force. And so, to be a little more clear, we're starting, like we have work AB. So we start at point A, end at point B. So delta U, that would be UB minus UA. So this is how we define potential energy. Let me write this down over here. I'm going to make a note here. In this class, we're only going to talk about two conservative forces. Gravity and a spring force. So now later when you get into electricity and magnetism, electric forces are conservative as well, although you do have to be a little bit careful on that. There are certain cases where it's kind of, you just have to be careful how you define things. Like if there's changing currents or something, that can make things a little crazy. But again, not for us to worry about in this class. So we're going to define potential energy this way. And again, this is only due to a conservative force because the work connecting points A and B can be, you can pick whatever path you want and you're guaranteed to get the same result no matter what path you choose. So let's look at an example of, well, we only have two and we haven't really talked about spring forces yet. So let's start with gravity. So let's say we have an object that's a height h above the ground. Let's call that point A. Let's say we're going to drop it. And it's going to fall to the ground, which is at point B. So what we do is let's just write down this equation. So we have to calculate the work done by gravity as we're going from A to B. Now, say the mass is at some point, we have a constant force. I should point out that if you go back to Newton's more complete equation for gravity, that Gm1 m2 over r squared, that is a conservative force. But anyways, just sticking to something close to Earth, the displacement is down, the force is down, so this work is going to be positive, and it's just going to be, it's a constant force, so it's just going to be the force times the displacement, which is mgh. Yeah, we still have that minus sign. The work is positive, so we still have that minus sign. Now, let's take this equation and multiply by -1. So then we have UA minus UB equals mgh. Okay. So this relates how the potential energy changes as a function of height. Like h could be anything above the ground. Oh, well, actually, if we drop it into like a pit or something, it could be below the ground as well. H can be negative. There's no problem with that. You can have negative potential energy. So, in a sense, we haven't really defined potential energy. We're really just talking about changes in potential energy. Now, if you look in the book, though, there's a formula. For gravity, you have potential energy. It's simply stated as mgh. So how can we do that? How can we just give it a value? See, in order to define potential energy, it's related to work, which means we need at least 2 points. We have to calculate a path connecting 2 points. So we can talk about, the work done over some path, which depends on these 2 points. So how do we get rid of one of these and just say the potential energy is mgh? What we're doing is we're defining a ground level. We're just going to state that UB equals 0. And then that's it. Then the potential at some height h is just mgh. So if we plug h equals 0, then we get, let's go over here. If we plug h equals 0, we get u equals 0. So when we're on the ground, our height above the ground is 0, potential energy is 0. This is a convenient reference frame. We just pick a reference level to be 0. Now, if you object to that, say, well, what is it really? Well, we can show that it doesn't matter what your reference level actually is, because the only physical significance are changes in potential energy. So we're going to do that by, again, like, why do we care about potential energy? Well, let's talk about energy in general. The only kind we've come across now is kinetic energy. We also have potential energy, but there's actually many other forms of energy. Like, say, I've got this, before going to this example, you might have heard the term conservation of energy. And that is true. Energy overall is conserved. So you can say, like, the total amount of energy in the universe is fixed. It cannot ever change. That's a statement of conservation of energy. So let's look at an example. Here I have this object, and I drop it. It has kinetic energy until it hits the ground, and then the kinetic energy went to 0. So it kind of looks like energy disappeared. But it didn't actually disappear. Where did it go? Let's do that again. You might have heard that. Well, sound carries energy. It has to carry energy. It causes vibrations in your eardrum, and that takes energy to do. So there's sound, but mostly, most of the energy in a case like this goes into something called heat. Another example, better demonstration of heat, one that you could actually experience, although I'll just give a simple example. Let's say I give this a hit so that it's moving, and then we'll see it's going to quickly come to a stop. So it was moving, so it has kinetic energy, and then that energy seems to have all disappeared. But no, it turns into heat, and you could experience that for yourself if you were to, for example, if you have like a rope and just slide down. You probably know if you've ever done that, not a good idea just to hang onto the rope and slide down, because all that energy is turning into heat, which can actually burn you. And yeah, it can be rather painful. Or if you rub your hands together, you're using energy and it's converting into heat. You can warm up your hands that way. And so there's a lot of different forms of energy. You can also turn mass into energy. That's what happens in nuclear reactions. Interestingly enough, you can do the opposite. You can turn energy into mass. So you can concentrate energy in a very small location and it'll create particles that didn't exist before. They do that in particle accelerators. So energy overall, there's a lot of different forms and they can turn from one to another, but energy never disappears. Now, there's a statement here. We're going to find mechanical energy to be just kinetic and potential. So if there's any other form of energy, then this doesn't really apply. I guess another form of energy would be like, say you have a battery. You can connect wires and get a current. Currents carry energy. So where's that coming from? Well, that's coming from chemical reactions. So there's also chemical energy. Again, all different types. But we define mechanical energy to be kinetic and potential. And the statement is, if there are only conservative forces acting on an object, then the total mechanical energy is conserved. So, in general, energy is conserved, whether there's conservative, whatever forces are acting on it. Like here, energy is conserved. There you go, hit it. So yeah, I gave it kinetic energy, but that all disappeared. It mostly went into heat, maybe a little bit in sound. Friction is a classic example of a non-conservative force. When we think of that removing energy from the system, it goes to some other form. So let's look at this problem. Let's say we have an object at a height h and we just drop it and let it fall. We can solve this problem. Let's say we want to know how fast it's going when it reaches the ground. So the only force acting on our mass is gravity. We're going to ignore air resistance because, that's what we did before. Let's just say we're dropping an object from a height h. So I'll put these labels here. Okay, so first off we check the only force acting on it is gravity. We ignore friction for now. And so we have a conservative system. So our system is just this mass, and the only force acting on it is gravity, so that's a conservative system. So we can say the mechanical energy is conserved. So I'm going to write that as an equation. Energy at A equals energy at B. And again, we're only dealing with mechanical energy. So I'm going to write this all out even though we don't really need to. So kinetic energy at A plus potential energy at A equals kinetic energy at B plus potential energy at B. Now, in this case, we're just dropping an object from rest. Let's give some numbers here. Let's just say the height is 12 meters. And we want to know the velocity at point B. How fast is it going when it hits the ground? So that's what we're trying to figure out. Okay, so because we're releasing it from rest, the kinetic energy is A, and our potential energy is 0 because we said it is. Okay, now let's continue with this. The potential energy at A is mgh, and that equals a kinetic energy at B, which would be 1/2 m VB squared, we can cancel the mass out and say VB squared equals 2GH. And just for a check, let's compare this to what we've done before. Let's just call down our positive direction. We say this object accelerates at a rate g, and because that's a constant, we can use this kinematic equation. So that's our basic equation. Applying to this problem, the final point, we say VB squared. V naught is 0 because we're starting from rest. The acceleration is g, and delta x, the distance fallen, is h. So VB squared equals 2GH. We're getting the exact same answer, whether we're using, Newton's second law to get the acceleration, and then kinematics, or using conservation of energy. But now, just in case you're not convinced that, we're justified in saying that UB equals 0, fine. Let's say the potential energy at the ground is 1 billion joules. And let's apply conservation of energy in this case. Now remember previously, let's do this part first, see if I can fit it here. We can consider a path from A to B and say UB minus UA, and that's equal to minus mgh. So just going back to our definition. Its displacement is down, force is down, so the work is positive, but we have a minus sign just from the definition. And so let's solve for UA, the potential at A. So just moving things around, we get the potential at A is equal to the potential at B plus this term mgh. So now let's apply just like we did before. We'll write this down, kinetic at A, even though it's 0. So we set it up exactly as before. Kinetic at A plus potential at A equals kinetic at B plus potential at B. Kinetic at A is 0, but now our potential at B is 1 billion joules. Well, what's the potential at A? That would be UB plus mgh. And so again, it doesn't matter what we set UB equal to, it's going to cancel out. And we'll get the exact same result we had before. mgh is equal to 1/2 m VB squared. And so yeah. So again, you're free to define your reference level to be anything. You can call it 0, or you can call it 1 billion joules. It doesn't make any difference at all. Okay. So, what is the point of conservation of mechanical energy? Basically, it allows us to solve a problem that we already knew how to solve. So far, you might not be seeing too much good out of this. But let's look at a different example. Let's say we're going to push, or just let an object slide down an incline. And again, we can only use mechanical energy if there's no non-conservative forces. So here, let's get rid of friction. And in this case, conservation of mechanical energy is valid. So let's say we start at the top of the incline at point A. We end up at the bottom of the incline at point B. And we just release this. We want to know how fast it's going when it reaches the bottom of the incline. Now the question is, can we do this with Newton's laws and kinematics? And the answer is yes. Basically what we'd have to do is we'd have gravity here, and then we'd have to break gravity into like a component down the incline and find the acceleration down the incline, and then then use kinematics, because this will be constant, so we can use kinematics. So again, we could do this. We could figure out how long it's going to take, and like how fast it's going to be going when it reaches the bottom of the incline. Using conservation of energy, turns out is going to be a bit easier. So the energy at point A, there's no kinetic, but we have potential energy, mgh. So we need to know some way of calculating that either way, whether you were using kinematics or conservation of energy. We'd have to at least be given, maybe we'd be given the angle of incline and the length. So this would be like what you would do in lab. Or in lab, you just directly measure h. So yeah, it's really all we need. And then at the bottom, potential energy is 0, so we have 1/2 mv squared. And again, it's basically very quick to solve this problem. If all we want to know is how fast this object is moving at the bottom of the incline, it's pretty much 2 lines, and this first one you don't necessarily need to write down anyways. Yeah, we can see the mass cancels out, and we can immediately solve for VB. So that's, conservation of energy can make things easier. That's one advantage to doing this over the, Newton's laws and, kinematics approach. It can be easier. And one reason why is that energy is a scalar. It's just measured in joules. Energy does not have a direction. And so working with scalars is much easier than working with vectors. So that's one advantage of conservation of energy. Sometimes it's just easier, depending on what you're trying to do. Now, if we really wanted to know how long is it going to take for it to reach the bottom of the incline, this isn't going to tell us. So then we'd have to go back to Newton's laws and all that stuff. But depending on the problem, if you want to know the velocity, this is a much easier approach than breaking vectors into components, finding the acceleration, and then applying kinematics. Basically we can do this in one line and we're done. But there's another advantage that's really based on the idea that gravity is a conservative force. What if we have an incline that looks like this? So we start at the top of the incline, we're going to roll this object, this is level ground here. Now how fast are we going to be moving at point B? Now the question is, can we solve this problem using Newton's laws and kinematics? And the answer to that question is both yes and no. Technically, if you know the shape of this curve, like if we look at the cart at some point on the curve, remember the acceleration is g sine of theta, where sine of theta is like this angle of incline, but we can see that that's changing as we, as it's going down the incline. It starts out steep and then it gets more gradual. And so acceleration is changing, and so we cannot do this in this class. If you know calculus, this might be a solvable problem, although definitely not an easy one. For one thing, you need to know the exact shape of this curve. But with conservation of energy, no problem. All that depends on is a change in potential energy between points A and point B. Can we calculate the work along the path that this mass is actually taking? Again, that's a calculus problem. We can't do it directly, but if we want to calculate the work between these 2 points done by gravity, we can simply consider this path. A straight vertical line segment where the work done by gravity would be mgh, and then a horizontal segment where the work done by gravity is 0. So overall the work is mgh. Whether you drop it straight down or have it go down an incline that's straight or curved, it doesn't matter. The change in potential energy only depends on the change in height. So the speed at the bottom is going to be the same regardless of the shape of the path connecting these 2 points. Now, the time will be different. It'll take longer to go down this path than just dropping it straight down, but they'll have the same speed at the end. And so conservation of energy is a very, very useful concept. In an algebra-based class like this, it allows us to solve problems not only easier than we would otherwise, but problems that we could not solve otherwise. Like, we could not do this in this class even if I gave you the shape of that curve. So conservation of energy, very, very useful. And again, we're just talking about this class. It extends beyond that. It becomes more and more useful the more physics that you study. Now, there's one more thing that I want to talk about. I mentioned there's only 2 forces. We have gravity and a spring force. Now, spring force, we haven't talked about those yet. Let's say we have a spring. Let's say one end is fixed. And we have a spring that's just at some natural length. Let's say this end of the spring, let's call that at x equals 0. Now, how a spring works is, let's say I grab this end and pull it. So I pull it over here. Say there's a mass at the end of the spring. So I pull it to the right. Well, obviously, the spring is not going to like that. It's going to try and pull back. So if you pull it to the right, the force is going to be to the left. Similarly, if I compress the spring, it's going to want to expand again. So if you have a spring and you compress it, it's going to push back. So the force is always back towards this equilibrium length here, where like the natural length of the spring. And it turns out that the force for a spring is proportional to its extension or compression, either way, the displacement. Whether you extend it or compress it, the force and magnitude is going to be proportional to that length. So in general, we can write the spring force as minus kx, where k is a constant, and that constant depends on the spring. It's very, if k is very large, it'd be a very stiff spring, something like you might find in the suspension of your car. Where if it's a very low value, then it's much easier to stretch it and compress it. So, like in a pen or something, there's springs in those. So, so this minus sign, like say x is positive, we pull it to the right, then the force is going to be negative. It'll be to the left. Now, if we compress it, x is going to be negative, and then the negative, or the minus sign times that negative x is going to be a positive number, so the force is going to be to the right. So this gives us both the magnitude and direction of the force. And again, you might wonder how important are spring forces actually. Turns out they're extremely important. Springs have their uses, of course, but this goes way beyond just springs. This is called the spring force, but a lot of real materials act this way. Now, I should point out, springs don't always really act perfectly like this equation is describing. There's like no fundamental law saying springs act like this. It's more of a very good approximation, provided you don't stretch it or compress it too much. There might be an extension. If you pull it too far, it's going to break down. And then a point where if you pull it, you're going to deform the spring entirely, and it's just never going to reach its equilibrium length again. But there are many systems that obey the spring force. And so it turns out to be much more important than it might seem. And in a sense, almost every force, to some approximation, actually obeys this spring force. Kind of an interesting thing. But anyways, let's go to, the spring force is conservative. So again, if, like say we have, say we attach a mass, and the mass is going to move down. the spring force is going to be up. And so the work done by the spring force is going to be negative. Which, remember the way we define potential energy, would result in a positive energy stored in the spring. But then if we return it back to its initial length, we'll get that energy back. So, we started, let's say this is y equals 0. Let's say it's in equilibrium here. So if we pull the spring down, so if the mass is underneath y equals 0, spring force is always going to be upwards. So when we pull it down, the spring force is doing negative work, but then when it moves back up, it's doing positive work. So if you return it back to its starting point, the work done by the spring force is going to be 0. Same would happen if you lifted it up and dropped it. So this is another example of a conservative force. Now the problem is calculating the potential energy, not quite as easy as it sounds. Let's just plug in. Let's just look at the magnitude here. The spring force is equal to kx. So let's say we have a spring and we move it through a distance. Here's our spring. Let's say we attach this mass and we pull it through a distance d. So let's calculate the work done by the spring force, just the magnitude. Now when it's over here, this is a wrong way to solve this problem. So we extended a distance d where the force would then be k times d. And then we multiply it by the displacement, which is d. And we get kd squared. This is wrong. The reason why it's wrong is because the spring force isn't always k times d. Over here it's 0, and the farther we displace it, the stronger the force gets. And so, yeah, this is complete nonsense. So let's say we plot the force as a function of displacement. It's going to be a straight line with a slope, not 0, but it's going to start at 0. The force at x equals 0, 0. It's in equilibrium here. Let's say we go up to some extension d. Now, if we have a constant force, let's plot that for a moment. Say we have a constant force, and we apply that through some displacement delta x. Remember, for a constant force, the work is equal to the force times the displacement. And we can see in this example that that would just be the area of this rectangle. And the exact same thing is going to apply in general, even if the force is not just this horizontal line like a constant force. If you have an arbitrary force, let's say you have a force that looks like this. The work is going to be the area underneath that curve, regardless of the shape of the curve. So to find the work for the spring force, we need the area underneath this curve here. So again, if we extend it to a distance d, the force at this point is going to be k times d. And so the work is the area of this triangle. So we have 1/2 times the base, which is d, times the height, which is k times d, or 1/2 k d squared. And in general, d is just like the extension. In general, though, we don't have a particular distance in mind. We just say we extend it a distance x. And so for springs, the potential energy function is 1/2 kx squared. And so that would be energy that's stored in the spring. Like an example of this. Let's say we have we actually do have these in lab. We have these projectile launchers where you have a spring inside, and you can put this tennis ball, this little plastic ball in here, and then you can press it. And so the spring becomes, compressed, and it stores energy there. And then there's a trigger that releases the spring, and it's going to expand and launch this projectile. They're called projectile launchers. That's one lab we sometimes do, but we didn't this semester, where you launch these projectiles and study projectile motion. But it's a good lab. It's just, can't do them all. But anyways, yeah, and you could use conservation of energy to find out how fast this ball is moving. It's, whatever stored energy there is in the spring, that's going to be converted to the kinetic energy of the ball. So you would need this formula to, figure out how much energy was stored in the spring. Now, we'll do some examples of these in class, but as far as covering the materials concerned, actually there's one more topic I'm just going to mention briefly, and that is how would we deal with the real world, where there's non-conservative forces. So let's just look at this as an example. And this is a good example because this is actually a solvable problem. Let's say without neglecting friction, could we apply conservation of energy to this problem? Let's say we have a mass on an inclined plane. We want to know how fast it's going to be going at the bottom of the plane. So we need to know like the coefficient of friction and the angle. We need to know all that stuff to solve it. But can we use conservation of energy? Not exactly, because friction is involved, which is dissipating energy. But we can use the idea behind it. And let's just set up the problem. We're not going to actually fully solve it. We'll probably do something like this in class. But say we start at A, end at point B. We can no longer say that EA equals EB. Yeah, that is no longer true. The mechanical energy at B is going to be less than the mechanical energy at A. I think it's easiest to see if we look at a numerical example. Let's say we have 1,000 joules of energy at A. But we know friction is going to carry away some of that energy. Let's say the work done by friction, and I'm going to take the absolute value here, the work done by friction is, say, 300 joules. Now we know that the work done by friction is negative, so just the magnitude of the work done by friction is, say, 300 joules. And so the question is, how much energy do we have at B? Well, if we started with 1,000 and we lost 300, then we know the energy at B is 700 joules. So we can still apply these concepts of conservation of energy if we know how much was lost. Just think of it as accounting. Energy never disappears. So if you start with 1,000, if you lost 300, there has to be 700 left over. That would be the energy at B. So that raises the question, how do you know how much energy was dissipated from the system? And in this case, we could calculate that. The work done by friction would simply be, let's say the length of the incline is L. It's going to be negative, so let's take the absolute value. That would just be the force of friction times L. And we can calculate the force of friction. That would be mu times the normal force. And then we have to find the normal force. So remember, we have gravity downwards. This component would be mg cosine theta. And the normal force would have to balance that. So this would be mu k mg cosine theta times L. And so this is something you can calculate. Now, if you have a different shape, that would be much more difficult to calculate. And in some cases, it's not really realistic to be able to calculate how much work was done by friction. But there may be some problems where you can actually get this number, but a lot of times I would tell you, like if I was giving you a problem, I would tell you, say 400 joules was lost due to friction, and then you could just set up. Whatever you start with, that has to be accounted for. So if you lost 400 joules, then you'd have 600 left at the end. So that's how we would handle these. Those are called non-conservative forces. So in whatever form they take, you'd have to know. And usually I would tell you, I just give you the amount. So just think of it like an accounting problem. And yeah, that'll be it for this one.